When we look at uncertainty, it is not defined enough to pin it down to a single point, so we look at a range of values. The reporting format and notation communicates this range of values. Our notation for measurements and their uncertainties takes the following form. Measured value plus or minus uncertainty, proper units. Where plus or minus is denoted as plus or minus. There may be circumstances where uncertainty will need to be expressed in a general form without numbers. We can do this by denoting uncertainty with the Greek letter delta that is placed in front of a letter to indicate an uncertain value. This takes on the form x plus or minus delta x or y plus or minus delta y. Measurements can also be reported in the following form below. X delta x less than x plus delta x. Uncertainty needs to be congruent with the measurement reported, meaning the point of uncertainty is in the same place as the last reported number in the measurement. Let's look at some examples. Notice there is congruence in decimal places with the measurement and uncertainty. If we report a measurement to the limits of the device, it would only make sense to report the uncertainty range in the same place as the last number reported. If the measurement is out to the tenths place, 2.4, then the uncertainty is at the tenths place, 0.1. If the measurement is out to the hundredths place, 2.40, then the uncertainty is at the hundredths place, 0.01. If the measurement is out to the thousands place, 2.400, then the uncertainty is at the thousands place, 0.001. You can see the pattern that the uncertainty and measurement decimal places match. The decimal place of the uncertainty should always agree with the measurement decimal place. It would be nonsense to write something like 2.400 and claim to be accountable for a correct measurement out to the millionths place plus or minus 0.000001. The decimal placeholder is not congruent and there is a serious gap between the recorded number and what is claimed to be certain. How could we account for the gap between the thousands place 2.400 and the millions place 0.000001? The measurement 2.400 cannot account for anything beyond the scope of the thousands place. 0.000001 is saying we are certain up to the 1 millionths place. On the other hand, we would not want to make a measurement of 2.400 with an uncertainty of 0.1. These are important details. This could be something that is overlooked, and recording a measurement like this may provoke judgment of being lazy or incompetent. Implied uncertainty. There are cases where uncertainty is not clearly indicated. There is no indication because it is common engineering and science practice that the last number is uncertain of plus or minus 1 unit by default. We have already covered how the last number of a recorded measurement is a default estimation. As such, it would only make good sense to assign the last number of estimations as a place where uncertainty lies, since this is where we placed a value outside the bounds of what was certain.